Morning everyone. I just wanted to take an introduction to whatever Rishikesh is going to do. We start off with a few basics and then we go into the details. So, cardiac output is basically stroke volume multiplied by the heart rate. And why do we need it? We need it so that we can actually do the goal-directed therapy. If the patient is not doing well in the theatre or in the ICU, what do you do? Do you give vasopressors? Do you give volume? Do you give inotropes? Or do you put a balloon? Or do you put the patient on ECMO? So, just to have an overview, what is it? So, we'll start off with the Ohm's law. Right? The Ohm's law states that V is equals to IR. I'm just giving you a basic, it is not the monitoring will come later on. You should know V is equals to IR. So, this applies even in the cardiac system. So, V would be the difference in the pressures, right? For example, supposing we are talking about the systemic circulation, there we have a thing which is called as the MAP. From the LV, the systemic pressure, and goes back to the CVP. So, there is a pressure difference between the MAP and the CVP. So, this would be MAP minus the CVP. Correct? Okay. I would be the cardiac output and R would be the SVR. So, if we have to calculate the Srindik, please close the door. Settle down. This is front here. I was just discussing regarding the voltage. So V is equals to IR. So V would be the voltage difference. This principle works. So voltage difference means that we have to calculate the systemic circulation. We have to calculate the MAP minus the CVP. I is the cardiac output, R is the resistance. So when we have to derive values from the monitoring, we have SVR, we have PVR, we have SVRI. What does this mean? This means that to calculate the resistance, if we have the cardiac output, so resistance would be SVR would be equals to MAP minus CVP divided by the cardiac output, right? And anybody can tell me the units for SVR? Mahesh, any idea? It is dynes per centimeter minus 5. Okay? Centimeter minus 5. Normal value would be around 900 to 1500. That is the normal. Right? And similarly, we can calculate it for PVR. What is pulmonary vascular resistance? Similar thing. We have the heart, right? We have the pulmonary artery going on back to the left atrium. So, we take the PM mean pressure minus this is the LVEDP, right? That is the pulmonary arteries and occlusive pressure, जो हम बेच करके देखते हैं, divided by the cardiac output. Similar, we have the PVR, right? And this would be again the same, and it is something like around 100 to 150. We take up the values, 200 tak mante hain jab okay, right? Good unit into 80 is the conversion factor here, right? So I'm just giving you a brief overview so you know what is a mean arterial pressure, you know what's a cardiac output, you know what's a cardiac index. If we divide any of these values with the body surface area, you have the index, correct? So we have the SVRI, if we divide by the BSA, we have the SVRI and we have the PVR. So this is what we need to reach. So this is what we have the basic concept of what are we looking at and why are we doing the cardiac output. Okay. The next thing, how do we measure it? There, actually I'm taking this class before that when Rishikesh starts so that you have an idea. the basic thing, the principle which was used initially was the fixed principle, in which they said that moving. It's okay. We use the fixed principle which can calculate the flow to any organ, which is defined by amount of oxygen consumed or CO2 produced divided by the arteriovenous difference between the content, right? So this is VO2 divided by oxygen consumption divided by the C, and this is CVO2. So this looks very okay that we can calculate it, but when you start calculating it, we need advanced spirometry, oximetry, and it's very difficult to know this value. You have a basic value, 250 ml per liter per minute, right? But this is not fixed for everything, right? So we make a lot of assumptions, and we are not accurate in calculating. The fixed principle, yes, we study, but actually do we use? We don't. The examination purpose, you have to write the fixed principle, and we can calculate this for any organ. So taking the body as an organ, we take the oxygen consumption in the body and total consumption divided by the arterial content. Anybody can tell me how much is it? 20 ml per 100 ml, and this should be around 15 ml per 100 ml. That would be 5. Correct? So we have the fixed principle. So just for knowledge sake, you must know it. The next thing, which is the most commonly used and the gold standard, is the thermodilution catheter. Right? In the PA catheter, it shows. I hope everybody has seen it once in CTVS. Yes. So we have a TD catheter in which there are two types. One is independent, one is continuous. In the intermittent one, we what do we have in a TD catheter? See, this is the heart. This is the catheter is floating. It is placed. When the catheter is placed, you look at the waveforms RA, RV, and it goes into the PA. Right. So we have a port here which opens at the at the right atrium, right? And at the tip of the catheter we have a thermistor, right? And we inject fluid, fluid comes here. It is at 0 degrees. It should be a very cold saline at 0 degrees, and then we see the decrease in temperature as it passes from here to here. You get it? So the idea is, if the cardiac output is more, the decrease would be faster. Correct? Agree? If the decrease would be faster, right? The decrease in the body temperature. It is not this 0 degree with already hai, right? So अब ये वाला temperature ये वाला है, that is a 37. ठीक है? तो कितनी जल्दी ये कम हुआ? 36.5 पे आया या 36.3 पे आया या उससे भी कम पे आया. We have to measure the rate of decrease, right? So for this, to calculate this, you must understand there is an equation called as the Stewart-Hamilton equation. You must be knowing about it. Let's look at it. What is it? So I'll start off very simply. Concentration is same as mass per unit volume. Correct? Any concentration is mass per unit volume. We divide both the things by time. We can divide both the equations by time. This is flow. Right? This is flow. This is C is equals to M by P. You get V up. V is equals to M by C. Correct? The volume per unit time is flow. Am I right? This is the mass of the injected, and C into T means this is the change in concentration with time. So what do you mean by that? For example, we take a dye, we inject it, and we measure it after it has passed through the circulation at a particular point, supposing in the femoral artery. I'll come on to that. So we make a curve saying that the concentration of the dye. So we are changing the concentration with time. Correct? So we have a graph which is similar to this. Okay? So the area under the curve, if we take an integral of this, the change in concentration with time, the integral of that will tell you, that will be this portion. So the cardiac output is inversely proportional to the integral of the change in concentration with time. If this graph is smaller, the cardiac output is more. फटाफट नीचे आ गया, same चीज. This is similar to the thermodilution graph. you can, instead of concentration, you can have a decrease in temperature here. Correct? Basic principle is how much dye do we put, or how much indicator do we put, how much cold saline do we put, right? This divided by the change in concentration, area under the curve of the concentration time graph, or the decrease in temperature versus time graph. Clear? Right? So when we do it for a curve, there are two different type of curve. This is one type of a curve. What I have explained here, the thermodilution one, in that we have this curve. There is no recirculation hump. You see this hump? This is not here. So in this, we have the formula is cardiac output is same as temperature of the blood minus the temperature of the injected multiplied by the volume of the injected divided by the integral of the change in temperature with time multiplied by a factor of 60 seconds ke liye hota hai. Okay, so we use this formula. We should have an idea basically to calculate the cardiac output. Correct? And in the thermodilution technique, in this, see, there are two ways. One is you put a cold saline and see the change in temperature first. Other is you put in a dye, है ना? इंडोसाइन ग्रीन डाल सकते हैं, लिथियम डाल सकते हैं, है ना? तो लिथियम डालते हैं, and lithium, then we see the change in concentration, and we have a recirculation hump here. Correct? So we have a recirculation hump here. So what do we do for extrapolation purposes? We just take the graph here and इसको देख लेते हैं, इसको छोड़ देते हैं. ठीक है? So we take the end of the curve here. So this is a basic principle of what do we do. है ना? I have derived the Stewart-Hamilton equation for you. I have told you that we see the change in concentration of the dye, or we see the change in the decrease in temperature, how fast it is. That will tell us the faster it is, the smaller the curve, the narrower the curve, and more the cardiac. So we have discussed regarding thermodilution or indicator dilution. Other thing is, there is a thing called as transpulmonary thermodilution. Right? GD, everybody understands thermodilution catheter by pulmonary artery catheter. We put in the we actually do it 3 times. And we take actually DD itself is a lecture. Thermodilution itself is a lecture in itself. It will take 40 minutes. So I'm just skipping it. We do it 3 times. We take the average value and then that's the gold standard, right? Next is a transpulmonary thermodilution. What do we do in that? In that, we ensure that we take the volumes. We don't measure the temperature difference here. We measure it in the femoral artery. And we don't give it through this. We put a central line, either an IJV or a subclavian, and we give the injected there. This travels through the RA, the RV, the PA, the LA, the LV, and goes to circulation. And the thermistor is placed in a special arterial catheter in the femoral artery. So the volume of distribution in this case, the transpulmonary thermodilution, is different, right? It is much more. So it is accurate, but not as accurate as the gold standard, the thermodilution catheter, the PAC. But it gives you so many things. You understand the difference? Here, it was given to the RA, measured difference in the PA. There, we give the injected, again in the SVC, again whatever, IJV or subclavian, and you measure where? In the femoral artery. So it travels through the entire volume of the body and it is measured there. Okay? So if it is measured there, we have various things which are get from the transpulmonary thermodilution. So what do we have? We have volumes which you are not get by the PAC. We have volumes. We have an idea of the end diastolic global volume of the LA, LV, RA, RV, a bit of the aorta and a bit of the pulmonary artery. Everything in the volume there, we can get that. That is called as the global end diastolic volume, GEDV. Then we have certain parameters which can be derived from it, which is called as the transpulmonary vascular permeability. or the extra volume, extra lung water, right? So in the critical care unit where we have to see all these things, we have to see whether it is pulmonary edema or it is the hydrostatic pressure is rising and there is some inflammation there. It will help to extra, whether to give fluid or not more fluid. For example, we see the pulmonary capillary bed pressure. We say this is high, we do not give fluid. But it is a fallacious thing. Why? Because the LV can be non-compliant. It could be ischemic LV. It should be a non-aortic stenosis LV. It is in sepsis, the LV is non-compliant. Diastolic dysfunction is there. So this will increase, but you might need to give the patient more fluid. So I am only trying to tell you that transpulmonary thermodilution is a different technique. It gives you volumes, it gives you extra information. GED बोलते हैं, global end diastolic volume, है ना? It gives you extra vascular lung water and it gives you pulmonary vascular permeability. Correct? So these are the extra things which you get from it. Okay? Right? Now, we have finished off with he will describe in some detail. These are beautiful slides. So I'm just giving you overview so that you don't get confused. One is thermodilution, other is transpulmonary thermodilution, and the third thing is, now every time it is very tedious, right? You put in a dye, and this is another way. Example, a dye dilution, I don't discuss that. Lithium, Litco monitor, right? The Litco monitor, what do? You don't put a central line. You put an IV line and we have a peripheral arterial special cannula in which we detect the concentration of the dye. So we give it IV, it circulates, we check the concentration of the dye and we make the same graph. And we have done away with the fayda kya? We done away with the central line. No PA catheter, no subclavian, no IJV, nothing. IV लगाया, dye दिया, नीचे देखा, graph बनाया, cardiac output आता. Correct? So that is one thing that this will have this graph. So we are using these techniques in which we use the stable Hamilton equation. Now it is tedious. Every time we have to give, it's an intermittent. We don't have. Then next time we find that something is wrong, we again give the dye. How many times can we give the dye? How many times? It has got its limitation. Litco method itself, lithium will have a toxicity. है ना? Patient is on lithium therapy. The neuromuscular blockers के साथ issue होता है. Correct? So limitations हैं. So we need something which will help us in the practical world. Every time we can't put in a PA catheter, every time we can. So we come to the concept of is a thing which is called as pulse contour analysis. Correct? So we have the arterial pulse. I'm sorry I can't rub this off, this is actually permanent. So we have a pulse contour analysis. So this is the arterial pulse and looking at the various ways to analyze it. So the many monitors we have the arterial waveform, correct? And they analyze the waveform and they estimate that this is systole, this is dichromatic notch, this is systole, and they calculate the cardiac output using this. Okay, obviously this is going to be inaccurate. Why? Because there are so many variables. The compliance of the arterial system. How is the old patient, the compliance is poor, and where it is measured. In aorta, the waveform is different. In the femoral artery, the waveform is different. Radial artery, the waveform is different. This will vary. Cardiac output doesn't vary like this. Correct? So, this is used in flow track, Vigilio, EV1000, right? And this system is used in this will if we use only the pulse contour analysis, for example in flow track or in Vigilio, what do? They take the patient demographics, right? And they say that they have a lot of data, proprietary algorithms, and they calculate the cardiac output based upon that. They do not measure it against the gold standard. The first thing, then we have monitors who said we will combine the two. We have a Litco monitor in which he takes the lithium, injects it, dilution method, we get the cardiac output, and then we calibrate, use this pulse contour analysis, right? Every system has got different ways of how do you go about it, different algorithms. Some uses the sine wave, some uses the root mean square method, there are quite a lot of them, right? So Litco does, Litco will also give the dye, they have the standard value of cardiac output, and then it's a continuous cardiac output is taken by this, and we calibrate it against the main value which we have got. So it is useful for calculating the trend in cardiac output. पहले इतना था, अब पेशेंट में कुछ हुआ एंड नीचे चला गया, क्योंकि पहले वाला हमारा कैलिब्रेटेड है, इस करके हम कह सकते हैं रिलायबल. करेक्ट. देन वी हैव दिस इज लिटको फ्लो ट्रैक. फ्लो ट्रैक में कोई कैलिब्रेशन नहीं होता, लिटको में होता है. लिटको में लिथियम डाइल्यूशन से करेंगे कैलिब्रेट. एक बना लिया, एक बार एक कर्व बनाने वाला, उसके बाद हमने इससे कंटिन्यूअस देख लिया कि ये आ रहा है और बार बार आपको कंटिन्यूअस टाइप ऑफ. थर्ड इज द पिको प्लस और वॉल्यूम यूज. दे यूज द ट्रांसपल्मोनरी थर्मोडाइल्यूशन टेक्निक, राइट. ट्रांस बताया था मैंने क्या है, प्लस दे यूज पल्स पार्टिकल एनालिसिस. उससे हमने वो कर लिया, वी फाइंड दैट दिस इज द बेसलाइन एंड वी कैलकुलेट इट अगेंस्ट दिस एंड देन वी यूज द पल्स पार्टिकल एनालिसिस टू हैव अ कंटिन्यूअस. Right, so we have two principles. One is we have the fixed principle. We have Stewart Hamilton equation in which we use thermodilution, we use integrated dilution, we have transpulmonary thermodilution, and then we have only this pulse control analysis as in flow track or Vigili or AD1000, and then we have things which will combine the two, Litco plus and Litco plus. Still people are not satisfied. They say we want more. We want non-invasive and we want more. So we have a thing which is called as minimally invasive. What do? We put a esophageal Doppler or we put a trans-esophageal echo. और उसमें क्या करते हैं? उसमें we have a supposing this is the aorta, so that is flow is there. We put a continuous wave Doppler across this, and we have a graph of the flow which is going. We calculate the area of the aortic valve, right? If we are doing a T, we calculate this area and we calculate the velocity time integral of this area. We combine these values, we have a cardiac output. Correct? I'm just going through everything briefly. Everything is a class in itself. That's why I said that the topic is too big. And esophageal Doppler, we put the Doppler in the esophagus, and we don't want to do a TE, it's too complicated. So what do? The sending aorta is there, we see the flow across this. Same thing. And we cannot measure the aortic valve area now. We assume, depending upon the various demographics, we assume that this area, this weight, this height, this is the right. So this is the minimally invasive. Then we come on to the non-invasive cardiac output. See, the technology is changing like this, right? In the last few years, so many monitors have come up which will tell you about the minimally invasive cardiac output. No, actually it is good for examination purpose and studying and academics that we have studied all this. Correct? Practically what is used? The non-invasive. But there are, actually it is very complex. I tried reading all of them and I tried memorizing all of them, but it was not possible. So what do? They, for example, there is a thing called as electrical bioimpedance, right? So what do? They place electrodes on the neck, two pair of electrodes here, two here, and two on this side of the manubrium sternum here, this portion. And then they see the change in impedance, as they say that as the blood flows across the aorta, there is a change in the resistance for the impedance across this. There are many problems with this. High signal to noise ratio. We have using cautery, put a central line, put an ICD, problems are there, correct? This goes. Then we have a thing called an electrical velocimetry. Then we have a thing which is called as, they put in a clear side, in the Edwards one, a clear side tire. They wrap it around the finger and they generate a arterial waveform from a non-invasive, right? And again the same pulse control analysis ka laga ke dekh liyo cardiac output, right? And there is something called a tonometry, which is a band again, and again they have. So they go on and on and on. There's a pram technique, right? So all these things can be used, but we have to calibrate it against the gold standard. This is the first thing. Secondly, they have been used mostly in hemodynamically stable patients. But once the patient gets unstable, septic, correct, requiring anatropes, all this fails. है ना, पल्सिंग सिग्नल ही नहीं आएगा, ठंडी हो जाएगी लिम्फ, ठंडी नहीं आएगी तो एवरीथिंग गोस, वो क्या करेगा, वो क्लियर साइड कुछ भी नहीं कर सकता, करेक्ट. So I give you a brief overview so that when you listen to the slide and when you listen to whatever Rishikesh has to say, he has worked very hard, and then you can understand what is it about, correct. Thank you, Rishikesh.